Today's SPSS teaching assistant is little Max. Little Max is the size of a kitten, but she is in fact 2.5 years old. She was just, I guess, the runt of her litter and never quite grew. Come on, turn towards the camera, little Max. Little Max constantly looks like she's annoyed with you or not understanding why she must be bothered by you. She's adorable. All right, bye, Max. So now we're going to cover how to run t-tests, etc. in SPSS. We're going to be using the monitoring the future data set again. So make sure you open that up. Make sure you'll use the data set that you created last week with that additional variable so that you can have access to more continuous variables, right? We created that attitudes towards drug scale. So that's another continuous variable that you can use as a dependent variable as you come up with your own research questions using t-tests or ANOVAs. So I'm going to replicate the same analyses that were in the lecture video that you've already watched. So we'll begin with the one sample t-test. The first thing we need to do is check the assumptions for the one sample t-test, which is independence of observations. We're just going to assume that when the data was collected, the participants were randomly selected from the population correctly, and that assumption has been met. A second assumption is the normal distribution of the sampling distribution of the variable. Because we don't have access to the sampling distribution, it's theoretical. We tend to look at the actual distribution of the sample and hope that the population's distribution looks similar. So to do that, we go under Analyze, Descriptive Statistics, and Frequencies. So for my first research question, it was, is the GPA of the sample the same as the average GPA of students? So the variable I want is grade point average, which is near the bottom. I select that and move it over into the variables box. And I want to get those skew and kurtosis scores to check whether it's normally distributed or not. And I can also select the histogram with the normal curve on top so I can visually see whether the distribution is normal or not. And I hit paste and I run the syntax. And here it is. So looking at my skew and kurtosis scores, I can see that the skewness is at negative 0.623, kurtosis is at 0.071. Both of those are within our -1 to +1 range. So we can say based on this information that the data is normally distributed. When we scroll down to the histogram, we can also again see that it more or less follows the normal curve. All right, so hopefully our assumption is met. Even if the skewness and kurtosis scores were really off, so say there was a skew score of 5 or something, because our sample size is 1,436, that's large enough that according to the central limit theorem, even if the population is not normally distributed, the theoretical sampling distribution will still be normally distributed when the sample size is large enough, and this sample size is definitely large enough. So assumption has been met. We are good to go. So to keep going, we're going to now run our actual test because we've checked our assumptions and they're okay. We're going to hit Analyze and then Compare Means. And this gives us all of our t-test options. The one we're going to select is the one sample t-test. We click on that and we need to move our test variable. So this is our dependent variable over, and that's GPA. We put that here in the box, and down here where it says test value, we need to put in what we're testing against. So we know that the average GPA for students is 3.0, so that's what we're going to test against. You can see that already the effect size has been selected for you, which is lovely. There's nothing you need to do under options or bootstrap. You just need to hit paste. And then you go to your syntax and you run it, and it pops up in your output. So the first table just shows us our descriptive statistics for dependent variable, grade point average. 1,400 students answered the question with an average of 3.11 and a standard deviation of 0.67 and the standard error of 0.02. And then we've got our one sample t-test results. Our t-statistic is here, 6.349. Its degrees of freedom, and then its significance level. Now, we've talked about this before. We only want to read the two-sided significance level, not the one-sided, because one-sided hypotheses are open to higher type 1 error. So we can see that the p-value is less than 0.001. So that means it is statistically significant. There is a difference between our sample of students and the test value that we tested against, that 3 average for the population. And the mean difference is 0.11. So on average, our sample of students has a GPA that is 0.11 higher than the general population of students. And we can see in the last table, the effect size, we will only read the one for Poens D, which has an estimate of 0.168. So this is your effect size, not the one that says standardizer. That's just part of the calculation. The actual effect size is the one that's labeled point estimate. So it is saying our effect size is 0.168, which is a small effect size. All right, so that's it for a one sample t-test. Let's now run our independent samples t-test. It's got the same assumptions, right? Independence of observations. We're going to assume we've met that through our data collection methods. Next, we need to check whether our variable, the dependent variable, is normally distributed for each level of the independent variable. So that means that for our research question about whether GPA varied based on alcohol use, yes or no, we need to check distribution for both those who answered yes and those who answered no. And the way we do that is with the split file command. So I'm going to hit data, and then I'm going to go down here near the bottom to where it says split file. I'm going to click on that. It's going to give me several options. I'm going to select organize output by groups. So this is going to allow me to check for the distribution of my dependent variable in several groups at once. So I'm going to select that ever tried alcohol. It's the second last one from the bottom. And I'm going to tell SPSS to organize my output based on these groups. And I'm going to hit paste on my syntax window and run it. Now, nothing is going to happen that you're going to see within your output until you run another test. So let's run the frequencies on the variable now to check whether it's normally distributed. We're going to hit analyze again, descriptive statistics, frequencies, and we want that grade point average again. It's basically the exact same syntax, right? Because again, we want that skewness and kurtosis, the rest isn't important, and we want to see our histogram with the normal curve superimposed. And we'll hit paste, find our syntax window, and run it. And now what you're going to see is that it actually has done it twice. So first, you're going to look at or sorry, in this case, it's going to run it 3 times because the first is for those who are missing on that ever tried alcohol, yes or no. So it's showing me the distribution for the grade point average for those who are missing, but they're not important because they're actually excluded from our analysis, so we can skip that part. And then ever tried alcohol, yes or no. These are the no's. 293 people answered both no and the GPA question. There's a skewness score of negative 1.18 and a kurtosis score of 1.24. So that's slightly outside of the limit that we have of -1 to +1. However, our sample size is 293. So that's quite large. Such a small deviation from normality is not going to impact our findings. So we don't need to worry about this slight deviation from normality and can go ahead and run our independent samples t-test. Then we look at for those who have tried alcohol. So that's 870 people, skewness score of -0.641, kurtosis of 0.240. That's perfectly acceptable. It's within our range of -1 to +1. So the grade point average for those who have tried alcohol is normally distributed, which is great, and our assumption has been met. Now, the important thing to remember is to turn off the split file command before you try running the independent samples t-test, or it's not going to work. You have to go back to data, click on split file again, and click on analyze all cases, do not create groups, and hit paste and run this split file off command. Very important. Once you've done that, you can now run your independent samples t-test. So click on Analyze, Compare Means, and Independent Samples t-test. You click on it, you get this box here. So we're going to put our dependent variable, our continuous variable, under test variables. So that's where that grade point average is going to go. And under grouping variable is where our independent variable is going to go. And that's our ever tried alcohol, yes or no. And we stick that in there. And you're going to see 2 question marks come up. You have to click on define groups to get rid of those 2 question marks. So what SPSS wants to know is within this variable, what are the codes for your 2 groups? If you're unsure, you can right click on the variable and then click on variable information, and that gives you those value labels if you don't remember them. So our 2 groups are coded as 0 for no and 1 for yes. That's exactly what we're going to tell SPSS. We're going to click on define groups, and we're going to say that group 1 is 0 and group 2 is 1, because that's the codes within our variable. And we're going to hit continue. And now those question marks have disappeared, and we have our variable 0 and 1. Ignore options, don't need anything there. Make sure that estimate effect size is clicked on the tick box, and we're going to hit paste. We're going to then run our syntax from the syntax window. And we get our results. The first table just shows us the descriptive statistics for each level of our independent variable. So the grade point average for both those who have said no, they've never tried alcohol, and those who have said yes, they have. So we've got an average of 3.34 for those who have not tried alcohol and 3.10 for those who have tried alcohol. The next table gives us our independent samples t-test results. Before we can read those, we need to check that third assumption, which is the homogeneity of variance assumption, right? Are the variances between the 2 groups roughly equal? And that's tested with Levine's test for equality of variances. So the F statistic has a significance value, and that's the important thing for us to read. If this significance value is less than 0.05, then we have to come to the conclusion that there isn't equality of variances, okay? The variances between the 2 groups are significantly different, and the assumption is violated, and we have to read the second row of numbers. But because here our significance value is much higher than 0.05, we can conclude that there is no difference between the two groups in their variances, which is good. That's what we want. It means that our assumption has been met. So that means we can read that first row of numbers, the one called equal variances assumed. And this is the T statistics that we report, along with this degrees of freedom and the significance value for the two-sided significance test. So we can see it is less than 0.001. So yes, there is a significant difference in the grade point average between those students who have tried alcohol and those students who have not. And that difference is on average 0.23 in their GPA score. Is this a meaningful effect or not? Now we look at the effect size to determine that. Again, we're going to focus just on Cohen's d. We're going to read the point estimate column. So the effect size based on Cohen's d is 0.354, and that's a moderate effect size. So we will make sure to report this number when discussing our results. I'm not going to cover the paired samples t-test because we don't have data that actually is appropriate for a paired samples t-test, but I'm happy to go over it in a tutorial or one by one with you if that's the kind of data you are interested in or want to run. What we will look at next is that analysis of variance, because it gets a little bit more complicated than the others. The first thing we're going to do is, again, check those assumptions for independence. We know that one is met. All of our observations are from a randomly selected sample of participants. We need to check the whether our dependent variable is normally distributed for each level of the independent variable. And we do that exactly the same way we did for the t-test. We go to data, split file, organize output by groups, and this time we kick out that ever tried alcohol. And the one in the lecture, the example I gave was level of happiness. So whether level of happiness changes what your GPA score could be. So we're going to group the output based on that level of happiness, and we're going to paste. We're going to go to our syntax window and run it. Again, nothing is going to show up in our output until we actually run the frequencies for, again, our grade point average, our statistics and charts. It already remembers what we did before, so we can just hit paste again and run it. And now we get here, you can see in this far left that we've got 3 different frequency tables for level of happiness. The first is for missing, which we don't care about because that's not actually part of our analysis. So we've got for not happy people, pretty happy people, and then very happy people. We've got 180 people who selected not happy as their option. The skewness and kurtosis scores are within our acceptable range of -1 and +1. So the happiness score or GPA is roughly normally distributed within this happiness level. And we can see the same for the pretty happy people. 945 people are pretty happy. Skew of -0.626, kurtosis of 0.079. Again, normally distributed GPA within the pretty happy group. And lastly, we've got the very happy group who has 304 people, skew of -0.685, and kurtosis of 0.271. Again, normal distribution. So fantastic, our assumption has been met. So we can turn off our split command, data, split file, analyze all cases, hit paste, find your syntax, run that one little line. And now we can actually run the one-way ANOVA. There's two ways you can run a one-way ANOVA. I've described both within the instructions for SPSS exercise 4. The first way, the simpler way, the one that I encourage you to use, is where you click Analyze, and again, you go to Compare Means, and you hit one-way ANOVA. See, it looks very similar to the t-test boxes. So where it says factor, that's where we're going to put our categorical independent variables. So happiness is going to go down here where it says factor. And our continuous variable, GPA, is going to go here with the dependent list because it's our dependent variable. So GPA in the dependent list. And then I'm going to select some post hocs, right? Because analysis of variance only tells us that there is a difference in that dependent variable somewhere between the three categories, but not necessarily where that difference is. So the post hoc tests will tell us exactly where that difference is. The standard one to select is Tukey. That's a pretty good one. There's over a dozen different post hoc tests that have been developed. You don't need them all. Just select Tukey. Tukey's great. It works as long as your homogeneity of variance assumption has been met. If that assumption has not been met, you need to select an option from down here where it says equal variance is not assumed as well. At this point, we don't know whether assumption has been met or not. So we're going to select both post hoc tests from the equal variance is assumed and one from the equal variance is not assumed. That way we've got our bases covered when we look at our output and find out whether our test of the homogeneity of variances is significant or not. So I'm going to select Games-Howell. That's a good standard post hoc test if the assumption of equal variances is not met. So you want to have Tukey clicked off and you want Games-Howell clicked off, and you're going to hit continue. Then under options, you need to select this homogeneity of variance test. So this is again that Levine's test that will tell you whether your variances are equal or not. And the other thing we want to select is these two here, Brown-Forsyth and Welch. They're basically very, very similar. They do the same thing. They are a robust type of ANOVA. So what that means is that even if you're not able to meet the assumption of homogeneity of variance, they take that into account and are still a valid test, even when that assumption is not met. So select them just in case the homogeneity of variance assumption can't be met. And we'll select this one here, the means plot, so that we can get a chart that shows us our results. We're going to hit continue, and we're going to hit paste. From our syntax window, we will then run our syntax, and here it is. The first table is that homogeneity of variances test, and we just need to read the first row, just the first row of numbers. So this is going to tell us whether or not we can assume that the variances are equal. As with the t-test, if this test is significant, that means that there is a significant difference in our groups and their variances. However, when we look at this significance column at the very end, we can see the value is 0.06. That's higher than our cutoff of 0.05. So these results are not statistically significant, and that's exactly what we want to see. It means that, yes, we have met our equal variances assumption. We can just read the standard results. We don't have to look at those more robust versions of ANOVA, like the Brown-Forsyth test. So the next table shows us our actual analysis of variance results. And the thing that's most important is this value here, the F statistic and its significance value. So we can see that it is statistically significant. It is less than 0.001. So yes, the grade point average does differ based on levels of happiness. We don't know where exactly, because ANOVA can't tell us that. Only the post hoc test can tell us that, but we know there is a significant difference. We can then look at the effect sizes to find out just how meaningful of a difference that is. And you want to read the first one, the eta squared. It is 0.036, so that's a moderately small effect size. If we go down a little bit more, you get your robust ANOVA results. So if my assumption of homogeneity of variance had been violated, I would report these numbers instead of the ones from the table above. But I don't need to do that because my assumption was met. So now we can look at our multiple comparisons for post hoc tests. The first one that is presented here is the two keys, honestly significant difference. That's what that HSD stands for. And then the second one is the Games Howl. So I'm going to read only the first part of this table because my assumption was met. I don't need the second half of it. And I can see that there's actually a significant difference between every single pair of happiness levels. So not happy versus pretty happy, there is a significant difference there that's statistically significant of negative 0.28 on average. So on average, pretty happy people have a GPA that's 0.286 higher than not happy people. And in my write-up, I would report every single significant difference. This last table here just shows you the three different averages that you have, showing that they are all different from each other, and then it plots them. One of the things that you might notice is wrong with this chart, which we learned about in our first week of class, is that it does not start at 0 on the y-axis. The y-axis starts at 2.80, which exaggerates the grade point average difference between our not happy, pretty happy, and very happy group. Do not, under any circumstances, give me this chart in your final assignment if you are running an analysis of variance. A much better chart can be obtained from our option 2 way of running an analysis of variance. And I'll show you that now. You click on Analyze, and then you click on General Linear Model, and then Univariate. Now, this looks a lot more complicated, but I'm going to tell you exactly what you need to click on, so it doesn't have to be too complicated. Dependent variable is exactly as it sounds. That's where you want to stick in your continuous dependent variable, which for us is that grade point average. Fixed factors is where you're going to put in your categorical independent variable, and the rest of these you're going to ignore. Next, you're going to hit on plots. This is what's going to give you that much better chart. It's going to list all of the independent variables here because sometimes you can have more than one. What you have to do is click on your independent variable, move it over into this box that has horizontal axis, and you're going to hit add. And now this is going to give you a line chart for our happiness variable based on grade point average. We're going to ask it to include the error bars because then we can see how our data is distributed. And we're going to ask for the y-axis to start at 0. That's very important, right? Because then our chart is actually accurately representing the data instead of exaggerating any differences between groups. And we're going to hit continue. We also need to hit post hocs because, again, we need to run analyses to find out exactly where the difference lies, if there is one. So you have to move happy into this post hoc tests for to tell SPSS, this is the variable that I want post hoc tests for. And it's exactly the same as with the other ANOVA. We want to select 2 key for equal variance is assumed. and Games Howell for equal variances not assumed. And then under options is where we would get our estimates of effect size, as well as our homogeneity tests. So those are the two options. You need to make sure you click under options. We're going to hit continue, and we're going to hit paste. Go to our syntax window and run our code, and we get these tables. Now, they're a little bit more complicated at first glance than the other way of running an ANOVA, but at the same time, they're basically the same. This Levine's test of equality of variances is the same. You're going to just read the first row where it says grade point average based on mean, and we see again, not statistically significant. Within the second table, you just need to find the row that lists your variable. So here's happy, our happiness variable, and that's the one we want to report. We can see again, it's the exact same F value to 26.29, and it's statistically significant, and we've got our effect size of 0.036. So with this version of running a one-way ANOVA, the effect size is given to you in the exact same table as the F statistic. With an F statistic, the degrees of freedom that you need to report, the degrees of freedom for the variable, so happy, there's 2, and then you also need to report the error degrees of freedom, so 1, 4, 2, 6. When you're writing this out in your write-up of the results, you put F, and then parentheses, 2, comma, 1, 4, 2, 6, close parentheses, and then equals to the actual F statistic. That's how that is presented. Again, check out the lecture PowerPoints from this week for exactly how to write that out. And then here we've got the exact same post hoc test results as with the other way of running an ANOVA, but now look at our chart here. Once we actually put the y-axis at 0, you can see that the difference in GPA between our 3 groups is really not as large as that first table indicated. So it is still different. There is still significant difference, but as we saw from the effect size, it is moderately small. It's not a very large difference. All right, so that covers our parametric tests. I will do the non-parametric tests in a separate video.